Welcome, everyone. I'm Jared Hanson, a senior product architect at Okta, and we're here today to discuss the keys to decentralized identity as part of the Future of Identity track at Octane 21. And as a reminder, we're live in the Q&A, so please feel free to chat any questions throughout this presentation. Let's get started. First on the agenda, we are going to define what decentralized identity is. In order to frame this definition, we need to understand the problems decentralized identity aims to solve. As part of that, we will take a brief look at existing identity systems, the challenges they face, and how they are evolving. Second, we will cover a bring your own identity use case that applies decentralized identity in the real world. We will use this scenario to examine the high-level aspects of how people, systems, and software interact to solve identity-related problems. Third, we will take a deeper look into the technology that powers decentralized identity. We'll examine the protocols being specified that will enable an interoperable ecosystem and highlight the industry working groups where these protocols are being defined. Finally, we'll take a look at the current state of decentralized identity. We'll cover why now is the time to begin preparing for decentralized identity, how we can make practical plans to encourage adoption, and what to look for as this technology matures. Throughout this presentation, we are going to compare and contrast decentralized identity to existing identity systems. At first glance, decentralized identity can seem daunting, as it represents a significant shift in how identity is approached. However, there are many areas where it reuses existing technology. We can take advantage of this to facilitate incremental adoption alongside existing systems. Of course, decentralized identity also introduces entirely new concepts and technologies. We'll examine these aspects in detail and highlight how they can be applied to solve identity challenges. And anything new has to be adopted in order to deliver on its promises, so we'll examine the barriers to be overcome. Let's dive in. In this first section, we are going to frame a definition of decentralized identity. In order to understand that definition, we will look at how identity has and is currently evolving in the face of present-day challenges. But before we define decentralized identity, we must acknowledge something. The truth is that there is no consensus about what exactly decentralized identity is. There is currently a tremendous amount of research, experimentation, and innovation happening in this space. There are hundreds of different organizations and companies pursuing projects, each with their own perspective on the problem. This is healthy for a new technology and what contributes to the promise of decentralized identity, but it also makes it hard to pin down. That being said, there is a common thread that runs through many of these efforts, so we can posit a definition. Decentralized identity gives individuals control over their own identity so they can decide how their personal information is shared and accessed, enabling trusted interactions while preserving privacy. The key phrases here are individual control and enabling trust. These are the problems that decentralized identity aims to solve. To understand why these problems exist and need solving, let's take a look at how identity has evolved. Identity has evolved through three distinct phases. First came decentralized identity. This was followed by federated identity. Now we are approaching decentralized identity. We are going to talk briefly about each of the first two phases in the following slides, highlighting how they work as well as the problems they create. It's these problems and the desire to solve them that lead to the next phase, decentralized identity. I want to pause here briefly and mention a minor phase, that of user-centric identity. User-centric identity took a detour from and back to federated identity. It was characterized by efforts including the original OpenID and Browser ID that attempted to apply federated identity in a way that gave individuals control. Even though these efforts failed to gain traction, the goals and lessons learned continue to influence decentralized identity today. We aren't going to cover these efforts further, but it is worth mentioning them now. Finally, I want to note that these phases of identity are not mutually exclusive. They can be and are deployed simultaneously. Decentralized identity will often be deployed alongside its predecessors. Centralized identity is characterized by using a username and password to sign into websites. As the first login mechanism used since the earliest days of computing to log into mainframes, passwords have carried forward through the eras, including PCs and LANs, to the internet and the web. Applied at scale on the web, centralized identity creates a massive password proliferation problem. People are forced to have hundreds of different passwords for each site they use, assuming passwords aren't being reused. If passwords are being reused, this creates a security concern as a compromise at one site can result in account hijacking at a different site in cases where the password is shared. This problem has two common solutions: password managers and single sign-on. Password managers give people the tools to manage hundreds of passwords, but don't address the problem directly. Addressing the problem directly brings us to the next phase of identity, federated identity. Federated identity arose as the web and software as a service were seeing broad adoption and the password problem was becoming acute. It takes a look at this problem and asks the fundamental questions. Why do I need a password for every site? Why can't I sign on once and carry that over to other sites? This gives rise to single sign-on, or SSO, which builds on centralized identity and allows people to use a single password or other set of credentials to sign into multiple websites. In this model, one website acts as an identity provider, or IDP. Users continue to log in to the IDP using their password, just as they would in centralized identity. Federated identity adds the ability for the IDP to convey login information to other websites, which are known as service providers or relying parties. This login information is conveyed in what is known as an assertion or a token. The assertion is digitally signed in such a way that the website can verify that the assertion came from the IDP and that the information within is valid. A website that relies on assertions from the IDP is said to have a trust relationship with that IDP. The term federation is a reference to this trust relationship and the fact that it is established between two otherwise independent domains. Federated identity is widely used in enterprises and often reduces the number of passwords an employee needs in order to access all their applications down to one. Indeed, this is one of Okta's primary products. In workforce scenarios, the IDP is managed by IT staff at the enterprise, and users are employees acting on behalf of the company. From a trust standpoint, then, there is a relationship between the IDP and the user, at least implicitly. In the consumer landscape, however, single sign-on is unevenly applied. Where it is available, it is characterized by centralized providers such as Facebook and Google. There are clear user benefits to this, as it makes sign up and sign in much more seamless. That said, users have very little relationship with their IDP other than as consumers. Consequently, the trust relationship, if any, implies very little. This gives rise to privacy and data protection concerns. Decentralized identity aims to rectify the privacy and data protection concerns, especially in the consumer landscape, by putting the individual in control. Control is enabled by shifting the transfer of identity information through the individual rather than directly between websites. This requires an ecosystem with additional infrastructure. To help us examine this ecosystem and the infrastructure it requires, let's apply a real-world use case. In this section, we are going to apply decentralized identity to allow people to bring their own identity. In the physical world, we are all familiar with the concept of carrying identification, such as a driver's license, passport, or employee badge. Throughout a day, or at least a pre-COVID day, we routinely present these credentials to people, a doorman at a bar, organizations, customs at an airport, or things, doorways in an office. Decentralized identity transforms these scenarios into the digital realm, allowing people to carry identification on their devices and present credentials both physically and electronically. Let's explore how Alice will obtain and use a digital passport. As we proceed through this use case, we will unpack the components within this ecosystem. We are going to start in the bottom middle with Alice, who uses an identity wallet and is our focal point in this scenario. We are then going to move to the top left with the United States, who issues a passport to Alice. From there, we will move to the top right and the airline that Alice presents her passport to. Then we will complete a loop to both the United States and Alice as the airline validates the passport. Alice begins her journey by installing an identity wallet. This wallet will typically be on her mobile device, as that is what she is most likely to have in her possession when needing to prove her identity to others. If Alice uses multiple devices, she can install a wallet on each of them so that her data is synchronized and accessible from whatever device she is using. This identity wallet will hold her digital passport, as well as the keys and other secrets needed in order to prove and confirm her identity. The identity wallet will be tightly integrated with the web browser and other applications on her device for use in online transactions. It will also be integrated with NFC and Bluetooth so that it can be used at physical points of presence. Conceptually, an identity wallet is similar to a password manager, but instead of managing passwords, it manages private keys used within decentralized identity. The first thing a wallet does is generate an identifier for Alice. This identifier will be used to identify Alice within the decentralized identity ecosystem in her digital passport. Ownership of this identifier is based on public key cryptography. As we've noted, Alice's identity wallet is responsible for storing the private key. It is also responsible for publishing the public key to a distributed ledger. As we walk through the rest of this scenario, we'll close the loop on how this key and the ledger get used. Now that her identity wallet is set up, Alice can request a digital passport. She might do this online by signing into her existing MyTravelGov account and clicking a button to get a digital passport. With one click, the passport is seamlessly issued and stored in her wallet using new web APIs. Let's take a look at what the digital passport looks like. Similar to a physical passport, the passport is issued by the United States and contains information about Alice. These bits of information are known as claims and convey Alice's name, date of birth, and other details. As this is a digital passport, it is accompanied by a digital signature. This digital signature is the equivalent of the anti-tampering mechanisms found on a physical passport. Once verified, the digital signature confirms that the passport was indeed issued by the United States and that the information contained has not been modified. Alice has her digital passport and she's now ready to take a vacation. She has booked a flight and is checking herself in at the self-service check-in kiosk. After confirming her flight details, she's prompted to present her passport. She grabs her mobile phone, selects the passport from the wallet, and taps her phone to the kiosk. Identity wallets can work just as easily in the physical world as they do online, just like mobile payments. What happens behind the scenes when Alice taps her phone to the kiosk? The software on the kiosk receives the passport over NFC and needs to confirm its validity. Just like in Federated Identity, the airline has a trust relationship with the United States. This relationship configures where to obtain the public key, which can be used to verify the digital signature on the passport. If everything checks out, we know that Alice has presented a valid passport. At this point, we know that Alice has presented a valid passport, but we are missing a crucial piece of information, however. How do we know it was actually Alice that presented it rather than an imposter? Let's take a closer look at the passport that was transferred to the kiosk via NFC. When the passport is presented, it is not simply a copy of the passport that was issued to Alice. The passport itself is encompassed with another digital signature from Alice's wallet, in what is known as a credential presentation. This digital signature can be triggered using hardware-protected keys with biometric unlock, just like mobile payments, giving full end-to-end authentication. Verifying this signature requires Alice's public key, however. Let's examine how that is obtained. Validating the signature on the passport presentation brings us full circle, back to Alice's identifier and the public key her wallet registered on the ledger. Just as it did when using the United States public key to verify the passport itself, the airline retrieves Alice's public key from the ledger and uses it to verify the passport presentation. We'll examine this in more detail in the next section when we dive into technical details. The introduction of a ledger on which individuals can register identifiers and public keys enables new opportunities. Alice can now issue self-signed credentials, statements about herself that don't need to be made by a third party. This capability was previously unavailable to individuals in federated identity systems because people don't have cryptographic keys. Only websites do. Cryptographic keys are a necessary requirement in order to make verifiable credentials or assertions. Self-signed credentials in turn give rise to the notion of self-sovereign identity, in which the individual is in full control over their identity, without the need for an identity provider. You'll often hear self-sovereign identity used interchangeably with decentralized identity. This presentation won't use this term, instead preferring the broader lens of decentralized identity, one in which individuals operate within an ecosystem that also contains third parties. Zooming back out, we have now completed the loop between all three parties, Alice, the United States, and the airline. This is known as the trust triangle. With that overview out of the way, let's define the roles a person or organization can play in decentralized identity. In this case, we have the United States, which is acting as an issuer and issuing digital passports. The airline is acting as a verifier and verifying digital passports. Alice is acting as a holder of a digital passport. Being a holder also implies she is a presenter of that digital passport. These same actors exist in federated identity, but the roles have different terminology. In this case, the United States would be referred to as an identity provider. The airline would be referred to as a relying party, and Alice is an end user. Note also that the assertion is transferred directly between the IDP and the RP. There's a maxim in identity that goes, identity is not what you say about yourself, but what others say about you. While this statement has broader, more philosophical meaning, it highlights the inability of an individual to speak for themselves within federated identity. When we map these roles into decentralized identity, the role of identity provider is decomposed into issuer and holder. Combining with shifting the transfer of credentials through the user, this effectively upgrades the role of the user to that of an identity provider. This allows individuals to now say things about themselves. This point is important, so let's restate the mapping of roles in decentralized identity in their equivalent federated identity terminology. The United States is an identity provider in both systems by virtue of being an issuer of credentials. The airline is a relying party in both systems by virtue of being a verifier of credentials. And Alice, who is just a relatively powerless end user in federated identity, now acts as an identity provider by virtue of being a holder and presenter of credentials. There is one more important aspect of identity systems, and that is which actors can assume which roles. In federated identity, IDPs and RPs can assume both roles. It is common, for example, that one IDP will function as a relying party of another IDP, the so-called upstream identity provider. This is typical when using social login for consumer-facing websites. Likewise, relying parties often function as identity providers. This occurs when the website has unique identity information or capabilities that need to be consumed by other applications. The user, however, cannot assume either the identity provider or relying party role. Once again, we see that the end user control is de-emphasized in this system. A similar pattern emerges in decentralized identity. Issuers can verify credentials, and verifiers can issue credentials. They can both also hold their own credentials. Users, meanwhile, can hold and present their own credentials. In addition, they can issue and verify credentials, both about themselves and about others. This is a direct result of giving individuals an identity backed by cryptographic keys, which was previously only available to identity providers and relying parties in federated identity systems. In decentralized identity, all actors can assume all roles and thus are equal peers with the same capabilities. With this analysis complete, we can now posit three keys to decentralized identity. 1, identity is derived from cryptographic keys. 2, identity shifts to a network model using a distributed ledger from a provider model. 3, all entities on the network have equal capabilities. The network is peer-to-peer. If you're like me, when you think of the implications of these 3 points, your mind immediately jumps to Metcalfe's law, which states, the impact of a network is the square of the number of nodes in the network. Federated identity has clearly followed Metcalfe's law and created a network with tremendous value. But if we examine it closely, the network it creates is predominantly between sites, between identity providers and relying parties. Users see network effects as well, but those effects are largely confined to silos within sites. There's a lot of unrealized potential here. Decentralized identity allows us to realize that potential by establishing a richer network with denser interconnections. The same connections between sites remain, but we can add connections between users of different sites, as well as between users directly. If this potential can be realized, the network effects grow by orders of magnitude. In this third section, we are going to dig a bit deeper into the technologies, protocols, and standards that enable a decentralized identity ecosystem. Just as we did when stepping through the digital passport scenario, our focal point will be Alice and her identity wallet. From there, we will discuss ledgers and how they operate. Finally, we will look at credentials. We will cover how credentials get issued by issuers and how they are requested by verifiers. We'll also examine how those credentials are verified, connecting the loop back to Alice's wallet and the ledger. Wallets are applications that people use to control and manage their digital identity. This entails 3 primary functions. 1, wallets manage identifiers and the cryptographic keys associated with those identifiers. In this respect, wallets are roughly comparable to password managers. 2, wallets manage public keys and other information published to the ledger. This is what enables a network model, allowing all people, organizations, services, and things using the same ledger to transact with each other. 3, wallets exchange credentials with issuers and verifiers. This is ultimately where the value of decentralized identity lies, as it allows for trusted, identity-enabled transactions. We've mentioned identifiers a number of times up to this point. Let's examine them in detail. Decentralized identifiers are globally unique identifiers that can be created without the need for centralized registries. In that regard, they are similar to UUIDs. What sets them apart, however, is that they are also resolvable and ownership can be proven via public key cryptography. We will come back to this a bit later. In terms of structure, all DIDs begin with the prefix DID colon. Next, they contain what is known as a DID method, followed by the unique identifier. The DID method in the middle roughly equates to the ledger the identifier resides on. In this example, BTCR refers to Bitcoin. The method also indicates how to resolve the identifier to its associated public key. We'll come back to this a bit later. We've already stated that decentralized identity shifts to a network model from a provider model. Comparing federated identifiers and decentralized identifiers highlights this fact. Here we have an identifier as it would appear in an ID token per OpenID Connect. A similar construct exists in SAML. This identifier was issued by an identity provider, in this case a university, and uniquely identifies the user, referred to as a subject, who is a student at that university. Importantly, this subject identifier is only unique within the issuer. In other words, identity is issued by a provider to the user. Furthermore, any use of this identity at other services is mediated by the provider. Contrasting that with the decentralized identifier, we remove the issuer and replace it with a distributed ledger. This is shared infrastructure, not managed by any single organization, which allows identifiers to be controlled and used by individuals without any intermediaries. As we've already seen, when a new identifier is created, a wallet publishes the corresponding public key to a ledger. Ledgers are a crucial piece of decentralized identity ecosystem, as they are what create a network-centric model. Any individual, organization, service, or thing that supports the ledger can interact with other parties that also support the ledger. This removes the need for identity providers as intermediaries. When people encounter distributed ledgers, blockchains such as Bitcoin and Ethereum are front of mind. Indeed, these two blockchains are the foundation of many decentralized identity projects. That being said, ledgers are not restricted to global blockchains, and many other topologies are possible. Sovereign is a prominent example of using a permissioned blockchain. Distributed file systems, such as IPFS, are also being used to underpin identity. Innovation is happening in so-called layer 2 overlays, including ION, which allow off-chain transactions backed by a layer 1 blockchain. A physical ledger isn't even needed at all. Peer-to-peer interactions can use ephemeral identifiers needed only among the peers without being registered in a broader context. As we detailed earlier, each ledger has a corresponding DID method. Individual DID methods specify how to publish, update, and deactivate an identifier on the ledger. They also specify how to resolve an identifier. Creating, updating, and deactivating an identifier is typically done by an individual through their wallet. Resolving an identifier is done by other parties, issuers and verifiers, as they interact with the individual. We'll cover resolution in more detail later. As we've noted, credentials contain a set of claims, which are statements made about an individual. Claims are made by an issuer and can be cryptographically verified using digital signatures. The validity of the signature, along with a trust relationship with the issuer, allow claims to be used as credentials. If the signature is valid and the issuer is trusted, use of the credential permits access to some service, such as a website, physical location, etc. From a standards point of view, decentralized identity has converged on a specification from the W3C called Verifiable Credentials. As the name suggests, it defines a way to issue and sign a set of claims, as well as a way to present those claims in a verifiable manner. It should be noted that while verifiable credentials are heavily used in the decentralized identity ecosystem, they can be applied outside of that as well. If you look closely at this example, you'll notice that the credential subject is using a DID, but the issuer is using a conventional HTTP URL. Verifiable credentials can be applied just as easily in federated identity systems. This is important as it opens up incremental adoption through hybrid, federated, decentralized environments. Comparing verifiable credentials with its traditional counterpart in federated identity systems is simple. They are directly equivalent to SAML assertions and JSON web tokens. The one new capability that verifiable credentials introduce is a presentation format in which the holder can be verified. With a standard format for representing credentials, the next piece of the puzzle is a way to exchange credentials. Credential exchange involves two steps. First, a holder needs to obtain a credential from an issuer. Either party could initiate this, with a holder requesting a new credential or an issuer offering a credential. Once obtained, a holder needs a way to present that credential to verifiers upon their request. In order to build an interoperable ecosystem of multiple issuers, verifiers, and wallets, standards must exist defining protocols for credential exchange. Unfortunately, there are currently no broadly interoperable protocols for credential exchange. Progress is being made independently in various groups, including Hyperledger Ares and the Decentralized Identity Foundation. Hyperledger Ares has arguably the most complete specification with their issue credential protocol and present proof protocol. The DIF is working on a presentation exchange proposal, which addresses half of the end-to-end exchange problem. These two groups tend to have a lot of cross-pollination, so convergence is likely. It should also be noted that once standardized protocols have been defined, there will also be a need for standardized APIs on top of those protocols. A W3C community group is defining the Credential Handler API for JavaScript applications in a browser. This follows a very similar model to how WebAuthn offers an API for underlying FIDO protocols. Given that a credential has been presented, the final step is verifying that credential, both the credential itself as well as its presentation. Once again, this closes the loop and brings us back to being able to resolve a public key from the ledger. Obtaining a public key returns us back to the decentralized identifier, and in particular, the DID method that defines how to resolve that identifier. Each DID method defines a ledger-specific way to resolve a DID to what is known as a DID document. This document is simply a set of metadata which contains the public key associated with the DID itself. This public key can be used to verify the credential. This DID document may optionally contain other information, such as pointers to services like messaging or file sharing that can be used to interact with the person identified by the DID. The decentralized identity community has broader ambitions of enabling things like personal data stores. Besides mentioning this here, we are not going to cover this topic in any detail. DID resolution in DID documents can be thought of as analogous to DNS. Just as DNS is a way to resolve a domain name to a set of metadata, such as an IP address, DID resolution is a way to resolve a decentralized identifier to metadata, including public keys. The difference is that DIDs do not require a managed namespace. Now that we've described how decentralized identity can be applied and taken a look at the technical components of the ecosystem, in this fourth and final section, we are going to examine the current state of decentralized identity and discuss paths to adoption. To start, why is now the time to be pursuing decentralized identity initiatives? There are three major factors driving momentum: privacy, data protection, and mobile identity. There's currently a major push, especially internationally, to protect consumer privacy. This includes GDPR in Europe, PIP EDA in Canada, as well as the CCPA in California. More government agencies are following suit with similar regulations as time passes. While these regulations are important for consumer protection, it is equally important for the industry to be proactively addressing these concerns. Decentralized identity gives us technology to enhance privacy. Hand in hand with privacy, data protection is increasingly a concern as breaches and misuse become more commonplace. This is illustrated by situations at Equifax and Cambridge Analytica. While decentralized identity does not offer a cure to these problems, it does offer tools that assist in addressing them. For example, if large troves of personal information, such as credit reports, can be stored directly on individuals' devices, rather than in centralized databases, we can eliminate single-point, high-value targets of malicious adversaries. Finally, mobile devices have become the predominant form of computing. This has transformed almost all aspects of how technology is used. Identity has been impacted as well, but is arguably still rooted in the web-based approaches of 10 to 15 years ago. We have an opportunity to make identity as simple as mobile payments. Just as Metcalfe's law highlights the promise of a decentralized identity network, we have to deal with the inverse of that equation. Bootstrapping a network is hard. We have a chicken and egg problem. Decentralized identity faces this challenge on multiple fronts. Not only do we have to deliver value to both issuers and verifiers, we also have to encourage individuals to adopt identity wallets. How can we start to tackle this in a way that doesn't sink massive costs into infrastructure before returning on the investment? First, let's shrink the network down and operate in company mode. Look for opportunities where the issuer and verifier are the same and an existing user base exists. Loyalty programs in retail settings or ticketing systems such as airlines are prime examples. In these scenarios, we can apply decentralized identity technologies such as verifiable credentials while leveraging existing investments in both centralized and federated systems. Adoption of more complex infrastructure such as distributed ledgers isn't necessary. This can speed deployment and lower costs. Next, look for opportunities within existing ecosystems that already have established partner relationships and governance or regulatory frameworks. Government, finance, and healthcare are all prime examples. We've already seen in our digital passport use case an example of interacting with government regulated industries. There are similar parallels in finance with the exchange of credit profiles and healthcare with the exchange of medical records. Once again, these industries can apply decentralized identity while continuing to leverage existing federated systems that, in many cases, already underpin these verticals. Finally, we need to collectively plan how to unlock global identity and bring the promise of improved privacy and trust to all individuals. This vision has a 5+ year time horizon and is going to depend on two key things: technical convergence and governance frameworks. As we've already highlighted, there are many efforts building out distributed ledgers to power decentralized identity. At current count, there are over 80 such efforts that have already registered DID methods. Each of these, in some respects, represents its own ecosystem with its own wallet, and there are little interoperability between them. While at this point this is good as it encourages experimentation and innovation, it is not sustainable long term to have a fractured ecosystem. Consolidation of ledgers and convergence on technical standards will be needed going forward. On the governance side, it is easy to address concerns within a company and within existing regulated industries such as finance or healthcare. As decentralized identity expands beyond those areas, however, we are going to have to define the parameters needed to assess trust. How is it determined? What situations and interactions does it apply in? What do we do when things go wrong? These are not questions that technology on its own can answer and will require involvement from social, legal, and political organizations. In order to help build towards this vision, the technologists, engineers, and developers in the audience are encouraged to get involved in efforts underway at the W3C, Decentralized Identity Foundation, and Hyperledger. The Trust Over IP Foundation is also doing important work, bringing together technologists with their social and legal counterparts to build out an architecture that accounts for both governance issues as well as technical issues. And finally, feel free to contact me via email at jared.hanson@okta.com or on Twitter at jaredhanson. We at Okta are very much interested in continuing this discussion and working together to build toward decentralized identity. Thank you for attending this session and enjoy the remainder of Octane 21. And we'll be around in the Q&A for the remainder of this session, so please feel free to continue asking questions. Thank you.